go. So the first requirement, of course, is that if you're going to have a relative minimum or relative maximum, then the number you're considering must be a critical number. So let f be a function such that f prime of c equals 0, or perhaps doesn't exist. I don't think that's really going to apply with the second derivative test. So that means that c is a critical number, so I'll just put Cn for critical number. So then here is the second derivative test, basically 3 parts. If f double prime is negative, that means that f is concave what? Yep, so f is concave down. Then f has a relative what? Max, yeah. So you can see that on that graph that I've drawn below, this would be a graph of f of x. And you can see that if at a critical number, the graph of f, if it's concave down, doesn't that have to be a high point? It's got to be. And so that's the first part. That's the first part of the second derivative test. The second part is if f double prime is positive. So if f double prime is positive, that means f is concave what? Up. There we go. Concave up on f. That would mean that f has a relative minimum. So relative minimum, this being a graph of f, you can see that the whole thing is concave up. And so any critical number you would have there would have to be a low point, a relatively low point. So relative minimum is what we would call that. So does anybody remember in what situation does the second derivative test seem to work best or easiest? When it's a polynomial. Or something very easily differentiated, right? So some kind of a polynomial, I would say second derivative test is far and away the quicker, easier option compared to the first derivative test. They both should work in most cases, but second derivative worth considering. So the final piece of this puzzle here is if f double prime of our critical number is 0, then the test has no meaning. The second derivative test does not tell you anything, and in that situation we can't use the second derivative test, so we should do what? Use the first derivative test. Go back to that. First derivative test should always give you a result as stated here. Sometimes the second derivative test does not. So let's do a couple of examples. So let's see. I'll just write that up here. Oops, that didn't work at all. There we go. F prime is equal to 3x squared minus 10x plus 7. There we go. Okay, so did you guys set that equal to 0? We're trying to find critical numbers. Okay, so we set that equal to 0. Probably factoring is the fastest way to proceed with this. Sydney, have you got to a point where you've solved that?
No.
Not yet? Okay, so work to get that factored and solved. I'll give everybody a chance to do that. We'll get our critical numbers and then we'll test them out. Did anybody go to the second derivative yet? Because you know we're going to do the second derivative test. Hayden, what did you get for that? Okay, so we'll use that in just a second. We'll come back to that. Okay, so if you factor it, sure. X equals 7/3. X equals 1. Does this make sense to the rest of you guys?
Yeah.
Okay, obviously skipping the steps there with the factoring, but assuming that you've done enough work. What's that?
Sorry, should I have done that?
No, I'm okay with that, right? I mean, you guys are all in a place where you've done a lot of factoring. So the idea that you could do it without showing all the steps there is feasible for sure. Okay, so then what's unique about the second derivative test is we don't create those intervals, right? What do we do with the critical numbers?
You put them into the second.
Yeah, we just take the critical numbers themselves and put them into the second derivative. So let's try it out. F double prime of 7/3. Alicia, what does that equal?
4.
4, yeah. And then we do f double prime of 1 would be the other one. Greg, what did you get for that?
F double prime of 1 is negative 4.
Okay, so we see that pattern. One of them is a positive second derivative. The other one is a negative second derivative. So we can do our conclusion here in a second. Grace, your question? Problem like this? I would say not. I would definitely approach this from you could do this without a calculator. Yeah. Okay, so conclusions. We would say then that f is, let's say at 7/3, is f minimized or maximized? Minimized, yep. So f is minimized at x equals 7/3. We've already proven that x equals 7/3 is a critical number. We did that at the very start. So we can now say because, how would you finish this? Because what? If we're using the second derivative test.
F double prime of 7/3 is positive.
Yep.
Making it concave up into the
F double prime of thirds is positive. So let's talk about where Alicia was going with that, because you said making it concave up. Obviously, we want to be cautious about the word it, right? So if you said, okay, making F concave up, that's perfectly good logic, and especially as you're trying to like kind of regain your momentum from last year when you were like really, really good at this. If you want to chain together the logic a little bit, so this means this, which that means that, therefore this or whatever, totally fine. But really what I have written up there is really all you need to say. If you can say F double prime of 7/3 is positive, coupled with the fact that we already knew that 7/3 was a critical number, then we know for sure that we have a relative min. What was that?
But wouldn't you also have to say that if they ask for an explanation that first that 7/3 is 0 at f prime and then...
Well, we already did that, right? We already proved that F prime is 0 when x is 7/3. So we proved that right here.
Don't you have to write it?
No, we already showed it right there. Our candidates are where F prime is 0. You're welcome to write that. You could say something like this: F is minimized at x equals 7/3 because F prime of 7/3 is 0, and F double prime of 7/3 is positive, which makes F concave up at x equals 7/3, making x equals 7/3 a minimum point on F. You could really chain that together. I'm just showing you kind of the bare minimum. Whatever you need to do to kind of like make it make sense for you and be logical for you, that's fine as long as you say it correctly. Avoid the use of the word it, right? But otherwise, I think we're good. All right, so the other one, of course, we would say F is not minimized at the other one. F is maximized at x equals 1 because F double prime of 1 is negative. Okay, questions, comments, thoughts? I want to make sure that that seems logical to you. Will, Michelle, Greg, this is at least newish to you. That seem logical? All right, fair enough. Well, so example number 5, less calculating to be done because it's just a graph, right? So take a look at example 5. I think that's our last one for this. So as far as just the x coordinates here, right? So it would be x equals -1, 1, and 3. Okay, so it does say justify your answer, so we've got to give that good reasoning to support that. Will, any thoughts on that? I'll start off where you started off. This is where, like, these points are where something happens, obviously, right? So -1, 1, and 3, those are definitely the correct x coordinates for the points of inflection. So, I don't know, Jared will start us off really well. This is, oops, let's go with this is where. There we go. This is where, Jared, do you know what happens?
Where G prime changes from increasing to decreasing or vice versa.
Well said. G prime changes from increasing to decreasing, and then you can just say or vice versa. We all know what that means. Or you can spell it out and say or decreasing to increasing. That works too. All right, so Jared, well said. Will, that makes sense. We can go back and like talk about why that is. For the moment, we can go back maybe a couple of pages in notes and see where that's kind of spelled out. You want to be able to prove inflection points exist by either using G prime like this, so it's smart to do it that way. Sometimes potentially G double prime as well could be used. So, okay, and then B. B says, where is the graph of G concave down and increasing like at the same time? Where do both of these characteristics apply? And again, we're going to try to justify ourselves or give a reason for what we said. So take a minute, look over B, see what you think. I have the advantage of having like a highlighter type thing. I'm going to look at this and say, all right, where's the graph of G concave down and increasing? Here's how I'm going to look at this. I know that G is increasing when G prime is positive. And since that's a graph of G prime, I'm thinking, okay, G prime being positive, that just means above the x-axis, right? So I'm going to highlight just above the x-axis. So anything in that area is now a candidate. I've really just excluded that little triangle, right? So if G prime is above the x-axis, doesn't that mean that G is increasing? Yeah? Okay, so I'm ignoring everything below the x-axis, so it's a small piece, but I'm ignoring that. What about this? How can we tell that G is concave down just from a graph of G prime?
If the slope is decreased.
Slope of what?
The slope of G prime
What did you say?
is negative.
Yeah. So if the slope of G prime is negative, then that would indicate G is concave down. Some other ways you could say if G prime is decreasing, saying the same thing as what Hayden just said there. So I'll just put G prime is decreasing. So I'll try to highlight those like this. So G prime is decreasing here and here. That's pretty much it, right? Looks like there's two intervals that'll work here. So the answers I'm coming up with would be -4 to -2. And 1 to 3. This would be my intervals there for those two characteristics. We good? Okay. So you could say there that you could say because G prime is positive and decreasing on those intervals. G prime is positive and decreasing at the same time. All right, we hanging in there? Okay, cool. All right, I think to say limits at infinity, right? No, so infinite limits are limits where the answer ends up being infinity or negative infinity. These are limits where the x value is approaching infinity. Yes, and behavior. Yeah, so there are two different things, infinite limits versus limits at infinity. My problem is with the word at. I mean, it's like I'm splitting hairs a little bit, but it is sort of a big deal. The word at, what does that mean? You're there, right? Like if I said, hey guys, I'm going to meet you out front. I'm at the front door. Does that mean that I'm almost at the front door? It means like I'm there. And so to say limits at infinity almost implies, I mean, it kind of does imply that we're at infinity. Really probably should be limit as x goes to infinity, something like that. But those are the forms right there. As Alicia said, we are talking about end behavior, the extreme right end, the extreme left end behavior. That's really all these are talking about. So take a look at the two graphs there. Nothing really earth-shattering about these. Take a look at the one on the left. So limit as x goes to positive infinity. We're looking at this one right here. On the left. So as we go towards as x goes towards infinity, we're talking about the extreme right edge of the graph. What does it appear to be that we're heading towards? -2, right? Yeah, the limit there would be -2. You're just really looking at a graph only to tell that. And then what about the other one? As x goes to negative infinity? 1, 2, 3. Was it 1, 2, 3, 4? Yeah, right? 4? Okay. Let's say that one reasonably looks like 4. Of course, we're basing all that on a graph. Really can't do any better than that based on our graph. Let's take a look at these two basic rules here as far as limits at infinity go, or limit as x goes towards infinity. So talking about this one right here, limit as x goes to infinity of c over x to the r. So x is some variable, right? R is some exponent, and c is a constant, right? So if the top is held constant at whatever constant, 1, 26, 10 million, whatever it is, and x is going to infinity, down there in the denominator, what is the overall value of this fraction heading towards is the answer to the limit? Going to 0, right? Going to 0. All right. And then kind of the same idea for the other one. We'd be heading towards 0, perhaps from the other side of the x-axis, maybe from the negative side, maybe from the positive side, who knows. But we'd be getting 0 for that as well, because if something is held constant in the top, and the denominator is increasing without bound, or for that matter, decreasing without bound, then the overall value of the fraction is heading towards 0. So one says limit as x goes to infinity of x squared plus 3 over 2x squared minus 1. And so the pre-calc trick is this. The pre-calc trick is associated with horizontal asymptotes, which is what really limit as x goes to infinity is. And the pre-calc trick is really simple. You just look at the degrees. So if you look at The degree of the top, the degree is 2, right? X squared. What's the degree of the denominator? It's also squared, isn't it? So whenever the degree of the top and the degree of the bottom are the same, then the end behavior is what?
It's the coefficient of the degree. We don't say the same, then it's 1/2.
Yeah, it's the ratio of the lead coefficients. Yep. So the top coefficient is 1, the denominator coefficient is 2, so it would just be 1/2. And in a multiple choice setting, why wouldn't you do that? Right? Makes no sense to overcomplicate it. I'll show you a process here in a second when we need to get there. But let's go ahead and think about these. It's just being efficient, right? Let's use that pre-calc trick. Like I said, I'll show you another method here in a second. Number 2, pretty similar, except the degree of the top is not the same as the degree of the bottom. What's the relationship? Top is less than. So if the top is less than, then the limit as x goes to infinity, 0. Whoever said 0 is correct. Okay, these can all be proven using this technique that I'll show you here in just a moment. But that'd be the answer. And honestly, in a multiple choice setting, if you took any more time than we just did to do those, you're definitely wasting time. So I would encourage you to use the little trick there. This is where the pre-calc trick sort of lets you down, right, a little bit in terms of what we're doing. Because in pre-calc, you said, okay, on number 3, the degree of the top is actually bigger than the degree of the bottom. Do you remember what you did in pre-calc?
Infinity.
Everybody loves it. Long division. Nobody loves it. Yeah. So thankfully we don't do long division here. Because long division you would get some kind of like crazy slant asymptote or quadratic asymptote or something like that. We're not just directly trying to find the asymptotes here. We're just trying to find the end behavior. So here's the actual process. Let's look at it like this. What you do is you look at the degree of the denominator. This will work for all these. What's the degree of the denominator? 1. So x to the first, right? So here's what we would technically do. We would write limit as x goes to infinity. And we would divide every single term, top and bottom, by that x to the first, right? So it would look something like this. We got our fraction bar. Instead of 3, I would write 3 over x. Minus, instead of 2x squared, I would write 2x squared over x. And then down below, instead of writing 3x, I would write 3x over x. And then minus, instead of just a 1, I would write 1 over x. So I divided every single term, top and bottom, by x to the degree of the denominator. This would be an actual process we could use to do this. There are other ways. This is one of them. So we do a little simplifying here. There's quite a bit. So 3 over x, we just leave it as 3 over x. But then the second term would just be 2x. Down here we would have 3, and then 1 over x. This is where that little rule we looked at a few minutes ago comes into play. Let's try to evaluate, this one here and this one here. If the top is held constant, but the denominator is going to infinity, what is that? 0. 3 over something or 1 over something getting super huge. The overall value of that fraction is getting closer and closer to 0. So I would say, we could do something like this. We could say, all right, well, when we apply the limit, this is going to 0. This is also going to 0. But that 2x definitely is not, is it? In fact, it's negative 2x. So if we look at the limit as x goes to infinity of negative 2x, what are we looking at there? What's 2 times infinity? Just a bigger infinity, I guess. I mean, that's sort of a bad way to say it. But then the negative times that would make it negative infinity. Yeah, so we get negative infinity over 3, poor 3. It's like a mosquito trying to stop a steamroller or something, right? Negative infinity over 3 is just negative infinity. And we'd be done. So like I said, that strategy of dividing by the degree of the denominator will always work. But I'd encourage you, where possible, like in examples 1 and 2, just use the pre-calc trick and you're good. Make sense? Okay. The final topic here is horizontal asymptotes. Taking a look here at y equals 2x squared over x squared plus 4. Sometimes they will actually ask this, like where or what are the horizontal asymptotes. So technically what you're supposed to do is treat this like end behavior, right? Limits as x goes to infinity or negative infinity, define horizontal asymptotes. So there's really 2 sides to it. Technically, here's what you're supposed to do. Limit as x goes to infinity of 2x squared over x squared plus 4. And then you're also supposed to do the left side too. Often they're the same thing. From time to time they are not. There was a question in 2008 on the AP test where if you went to the far right end versus the far left end, you got two different horizontal asymptotes. And like something like 97% of the people that got 5s missed that question. So they didn't count it. They just got rid of it. They said, we don't want that question. Must have been a bad question. Or it wasn't really a bad question, but people weren't ready for it. So you'd want to do both here. It doesn't really matter on this one. You really could just use the pre-calc trick to make this work. So what would you guys say? For the first one, we get 2. And because of all the squares everywhere, whether we're approaching we're approaching like infinity on like really big negative numbers or positive numbers, the squares are going to turn them all into positives anyway. So I think we'd also get a 2 there. So somebody's ready to go home. All right. So that's that for 3.5.